Hi, welcome back to the course Foundations for Machine Learning. Today we'll be learning about regularization. First, we will learn the theory behind regularization and then we'll implement it from scratch. You might have probably come across this diagram if you search on Google regularization visualized, or maybe in some other context, maybe you might have seen it on LinkedIn. And I must say that this diagram, which shows the difference between Lasso and Ridge regression, is very, very confusing. It's a beautiful diagram if you understand what's going on, but otherwise, I would say it's very, it probably makes you feel like you don't know what you're talking about. And but I have seen people use this diagram again and again. So we will try to spend some good amount of time today to decipher what exactly is going on in this, and how is this diagram showing the idea behind lasso regression can force some of the parameters to be exactly zero. On the other hand, ridge regression does not make it to be exactly zero, but approximately zero. So we will explore this idea. And once you are very comfortable understanding what this diagram is trying to say, I would say you have a fairly good grasp on regularization. So first of all, what exactly is regularization? It is a method used in machine learning to prevent overfitting. What is overfitting? Overfitting is when a model tries to learn complex patterns in data. Maybe the patterns in data are due to outliers. Maybe it's due to noise. When a model is trying to learn data, learn patterns in the training data, especially which may be outliers or noise, the model is not learning generalizable patterns. It cannot have very good results when you provide unseen data from your test dataset. What regularization does is it adds a penalty to the original loss function that the model is using, which discourages the model from learning these excessive complex patterns. And you will see this whole idea being visualized. So the basic premise here is that if you are discouraging the model from learning overly complex patterns, it can only learn the general trend in the data, and that may lead to a better model which can make better predictions on unseen data set. So what do we mean by generalizable pattern? Here is an example. If this y is your prediction and x is your data, so if your data looks something like this, then clearly, and assume this is the training data, then clearly this small waviness or small undulation is probably noise, or it's probably due to maybe a few set of outliers. What you want your model ideally to learn from this is a pattern that looks something like this, like an inverted, or rather like a bell-like shape. And in that case, if a new data point for x equal to a value somewhere over here is given, maybe the model can make a better prediction saying, okay, this will be the corresponding y value. So this is what your model should be learning, and not these individual rough patterns due to noise or outliers. So how do we do that? Because you know that machine learning models typically try to minimize their loss function, and it can minimize the loss function in training if there is a perfect fit between what the model predicts and what the data shows, right? So we will see how restricting the growth of certain weight parameters in the model can help you make more generalized predictions. How does regularization work? It works by adding a penalty term. So this is the penalty term added to your normal loss function. So whatever your loss function is, you add a lambda times penalty term. I will come to the format of what this penalty term looks like, but see what is happening here. If lambda, which is the strength of regularization, is 0, it means you get back the original loss function. The original loss function could be mean squared error. It could be any loss function that you are using in your ML model. And if lambda is a very big number, then your regularized loss is probably closer and closer to this whole penalty term, which is the product of lambda and the penalty. And what is the penalty term itself looking like? It is kind of like a function of the model parameters, which is theta. So your original loss function is a function of theta. Now you have L modified, loss modified, equal to L of theta plus lambda times penalty of theta. So this penalty function is a function of theta, which is the model parameters. Now, let's see the exact format of this regularization term in the context of two regularization techniques. First one is called ridge regularization or ridge regression, which is also called as L2 regularization. Second one is called lasso regression or L1 regularization. So in ridge regularization, the format of the penalty term associated with lambda is sigma W square. W is the individual weight term. So if your model has, if model is just a straight line, y equal to mx plus c format, then this is simply m square because you just have one weight term. If your model has multiple dimensions, I mean, if your data has multiple dimensions, for example, x1, x2, x3, etc., since I cannot draw more than three axes very easily or meaningfully, here I will say x1 is one of the dimensions of the data, x2 is another dimension, x3 is another dimension, and y is the prediction that is being made. And in this case, you will have model parameter terms, which is like y predicted equal to theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus some kind of bias term, which could be like a constant. Now, this is a linear regression with multiple dimensions being present. And here, if you look at the sigma wj square term, in this case, it will be theta 1 square plus theta 2 square plus theta 3 square. In a normal linear regression where you have just one independent variable and one dependent variable, where you have a data that looks like this, and this is y and this is x, and this being the linear fit, you have regularization penalty term multiplied by lambda equal to lambda times m square, where m is the slope of this line and this line is represented by y equal to mx plus c. mx plus c. So that is the lambda times sigma wj square term, the penalty term in ridge regularization. And if lambda equal to 0, you can already see that the ridge regularization or ridge regression is same as linear regression for this in this case. Here I have written mean squared error as the original loss function, which is used in linear regression. So yi, which is the original value, actual data point, predict actual value of y, which is supposed to be predicted by the model. But what model predicts is like something like xiw. So this is matrix multiplication, not like y equal to mx plus c in algebraic format, just in the matrix format. And this mean squared error sums up the error due to every single data point, which we have discussed a lot in the previous lectures. But now think about the case where lambda is large. If lambda is large, the only way to keep the loss function value, because now the net loss function is the mean squared error plus the penalty term. The only way to keep the sum total of mean squared error and penalty term small is to shrink the value of these weights. And if the value of weights are not small, so let's say lambda equal to 100, and if the weights are big, then you have a huge penalty term here, which means that the overall loss is very big, even if the mean squared error can be brought down to 0. So just bringing mean squared error down to 0, like how we do in normal linear regression, is not enough. So lambda has that effect, which is like controlling the value of the weights or the model parameters from overshooting. But please note, in ridge regularization or ridge regression, the weights can be shrunk close to 0, but not exactly 0. And this is a point where we will spend some time today, because I also, while learning about regularization, I had this doubt for a very long time. Now let us look at the second type of regression or regularization, lasso regression. it is called L1. So this is L2 because you are using kind of a square term of your parameters. Here instead you are using just an absolute value term. So everything else remains the same except the penalty term is lambda times sigma modulus of Wj. Previously it was sigma Wj square. So here again, if the value of lambda is very small or even zero, this lasso regression behaves basically like linear regression. If the value of lambda is large, then the model shrinks, just like how what the ridge regression does. Model shrinks the weight values to zero, and some of the weights will be shrunk exactly to be zero. So what does this mean? Some of the weights being shrunk exactly to be zero. This is what it means. In this example, where I showed you had three-dimensional data, you had the dimension I, j, k, for example, or x1, x2, x3, whatever you want to call as your three dimensions, and you are making a prediction using the data which has three dimensions. Imagine the case when you shrink one of these model parameters to be exactly zero. So theta 1 equal to zero, which means it's as if you are effectively removing the first dimension from the data. So you are reducing the dimensionality of the data from 3 to 2. You are now only considering the second and third dimension. So if the model parameters, if some of the model parameters are exactly assigned as zero, you are essentially performing feature selection, where you are saying the dimension 1, 2, and 3 are okay, meaning features 2 and 3 are okay, but I don't want feature 1. Now, here a natural question will come. How exactly does L1 regularization force some of the weights to be exactly zero? How is that happening? Because in ridge regression, we discussed that the weights are going to be approximately zero if the lambda value is large, but not exactly zero. In L1 regularization, in Lasso, I had written Lasso here, somehow it's lost. I'll write it here. In Lasso, the weights can be shrunk, some of the weights can be shrunk to be exactly zero, performing feature selection. How is this happening? And that is the question that we want to discuss next. Why exactly does Lasso set some of the weights to zero, but some of the weights to be exactly zero, but not ridge regression? If you can answer this question, or if you can truly understand why this is happening, I would say you have a fairly good understanding of regression as a whole. This is a simple question. You might think that this question is not really relevant in your understanding of regularization, because these formulas look very simple. This is not a complex, difficult to understand formula for Lasso or for ridge regression. So you might wonder, why does this understanding of weights being pushed to be exactly zero in Lasso, why does the understanding of answer to that question contribute to your deeper level understanding of regularization? We will see that in a moment. But please understand that although this equation looks simple, the first figure which I showed you today, this figure, it does not look simple. It's not easy to understand what's going on in this figure, right? So let's try to understand what's that. So I'm going to present here two ways to look at it. First one is a mathematical way to look at why some of the weights can shrink to zero. The second one would be a bit more graphical approach. Both of these approaches have been adopted, or I have borrowed it from some of the blog articles which I read. And one of the articles is this from the website called explained.ai. And I will really be failing in my duties to teach you regularization in a really good way if I don't talk about this article, or if I don't show some of the items that are presented in this article. So I'll be doing that also. So first, look at ridge regression, where I'm just simplifying the summation term in the mean squared error term. I'm just writing it as if you have only one data point and you are doing a line fit through that. So simply this term is y minus mx the whole square. The 1 by n times sigma, that part I'm just ignoring for simplicity. Not just that part, like just assume that it's just a data point. So y minus mx the whole square, because mx is now the least square fit, plus lambda m square. This is the ridge regression term. Now, if I want to find the optimum value of m, which minimizes the loss here, then essentially what I'm trying to say is dou loss by dou m. So L is the ridge loss, dou loss by dou m equal to 0. And you can easily perform a derivative here. So the derivative of this term, which is the mean squared error term with respect to m, is 2 times y minus mx times minus x. Then the derivative of this term, which is the penalty term with respect to m, is 2 lambda m. And you can set this to be 0. Now, the optimum value of m, we can eject out of this in terms of x, y, and lambda. So bring all the terms that has m in it to one side of the equation and rest of the terms to the other side of the equation. So that means I can write it as 2 times x times y minus mx equal to 2 lambda m. 2 and 2 can be cancelled, these two. And then I can write lambda m plus, then I can bring this term to the left hand side, lambda m plus x m x, which is mx square, equal to x times y. And then I can bring m common into outside, and then m times in the bracket I can write lambda plus x square equal to xy, which means m equal to xy divided by lambda plus x square. So what did we do so far? We defined the ridge regression loss, and we said that to find the parameters of the model, which is m, that minimizes this loss, we have to do dou L by dou m equal to 0. If dou L by dou m equal to 0, then we can say the optimum value of m equal to xy divided by lambda plus x square. Now, we were discussing that why exactly does ridge or lasso pushes the model weights to be exactly 0, but ridge cannot do that. Imagine if ridge were to push the model parameter m to be exactly 0, which means if this term, which is m, should be exactly 0 at the point where you're optimizing the loss, that means and xy is not 0, because then it will be a trivial solution. You're talking about non-zero x and y values, which means the lambda plus x square term should be tending to infinity. And what does that mean? Basically, lambda tending to infinity. So what this shows is that unless lambda tends to infinity, the model weight or model parameter m will not become exactly 0. It can become approximately 0. If lambda is very, very big, then m can become very, very small. So that is what this equation is showing, but not exactly 0. M will not become exactly 0. Now let us look at the other case, which is lasso regression. In lasso, the loss function can be written like this, where this is our good old mean squared error loss function plus the penalty term, which is lambda times modulus of m. It's usually the summation of modulus of m, but here we are assuming there is only one model parameter. If the m value is greater than 0, we have one type of derivative, and if m is less than 0, you have another derivative, because the modulus function has derivative equal to, so this is y equal to modulus of x, right? I mean, this should be at exactly 0, something like this. So if x is greater than 0, the slope is 1. If it is less than 0, slope is minus 1. So the derivative should depend on the value of the m itself. But if we say that, okay, we want to find the optimum value of the model parameter m, which will minimize the loss, it means we are saying the dou loss by dou m should be equal to 0. And what is dou loss by dou m if m is greater than 0? The derivative of the first term, which is mean squared error, is exactly same as the previous case. So 2 times y minus mx times minus x, plus derivative of this term will be, if m is greater than 0, modulus of m is 1. So this will become simply lambda. So this term should be equal to 0. And now we can bring all the terms with m on one side of the equation and all the terms without m on the other side of the equation. So we can expand this term and write as 2mx square equal to 2xy minus lambda, which means m equal to 2xy minus lambda divided by 2x square. Now, why did we do this calculation? Because we wanted to prove that for lasso regression, it is possible that for big values of lambda, you can push the model parameters close to 0. And let's see how that happens. So if the model parameter has to be exactly 0, then it can happen in so many ways. First of all, the numerator can become 0 if 2xy equal to lambda, which means for the values of lambda that satisfy lambda equal to 2xy, you have model parameter to be exactly 0. And what is that model parameter? Exactly 0. What does that mean? It also means that you are optimizing the loss function, because this equation is satisfied, this condition is satisfied when dou loss in lasso divided by dou m equal to 0, right? So you are automatically optimizing the loss function when the model parameter is satisfying this condition, and the model parameter itself can be pushed to be exactly 0 if 2xy equal to lambda, if this condition is satisfied. And there are many infinite combinations of xy equal to lambda by 2. You can find many xy pairs that can satisfy the condition xy equal to lambda by 2. So this is a mathematical way to see why it is why Lasso can push the model parameters very close to 0. I mean, to be exactly 0, whereas Ridge only pushes it to be close to 0 as the value of lambda increases, but not to be exactly 0. So here, even if the value of lambda is very high, you can still be m equal to exactly 0, because for even for very high values of lambda, you can find xy pairs which satisfies the condition. So even if lambda is 10 raised to 37, you can find xy pairs which satisfy xy equal to 10 raised to 37 by 2. In contrast, for the ridge regression, here, if lambda is very high, then m cannot be exactly equal to 0 unless the input itself is exactly 0. But for the case where the x and y are non-zero numbers, you can't find m equal to exactly 0 even for very high values of lambda. So this is a mathematical way to prove the idea behind lasso regression being able to do feature selection, because it can make some of the m values to be exactly 0. Now here you might have some confusion. I can foresee that. You might wonder, okay, here we are only using one model parameter, m, but ideally I should have shown something where you have 2 or 3 more model parameters and some of them getting suppressed completely to 0. But I hope you can, from this proof, you can probably extrapolate. You can write an equation like L lasso equal to y minus m1x1 plus m2x2 plus m3x3. So this is like 3 dimensions now. 3 features are there, m3x3, plus maybe a bias term. Maybe bias term we can keep it as 0 for now. This, the whole square, this is assuming only one data point, plus lambda times m1 square plus m2 square plus m3 square. This is the ridge case. And for, sorry, yeah, I wrote it as lasso here. This should be ridge. And for lasso, you will have modulus term instead of these terms. So let me just copy paste. For lasso, this term will be replaced with square will be removed, and you simply add the modulus of these model parameters. So this is lasso. And then you can do the derivative and kind of generalize whatever you found with just one model parameter, and whichever model parameter wants to be exactly 0, it is possible in lasso. Now let us come back to the graphical intuition part, which is where I am more excited to, which is what I'm more excited to show you, because this is a figure that you will definitely come across on internet somewhere when you type regularization on Google. So I want to spend some time on this. So for that, first let us assume a loss function. So here I'm assuming a type of loss function, which is L equal to x minus 3 the whole square plus y minus 0.5 the whole square. Here, please understand that x and y are model parameters. They are not input-output pairs. These are model parameters like theta 1 and theta 2. Okay? Maybe it's better if I write it as theta 1 and theta 2. But assume that this is of the form. Just understand that this is of the form theta L equal to theta 1 minus 3 the whole square plus theta 2 minus 0.5 the whole square, right? It's not like these are input-output pairs. Now, normally, if we are not doing any regularization, what would happen? Where do you find the minima of this loss function? The minima occurs when x equal to 3 and y equal to 0.5. Because when x equal to 3, y equal to 0.5, this entire loss function becomes 0. Whereas the minimum value possible is first of all 0 because these are squared terms. So you can't go negative. You can't have the loss to be negative. And for all other values of xy pairs, you will have loss to be positive number. So, and how does the loss function look like? So if loss is extending, I mean, projecting to the z-axis, then you can draw these iso contours of the loss function where along each of these circles, the loss function take one particular value. So in this graph, how do we represent, other than the original loss function term, which is this quadratic term, how can we represent the regularization terms as well? So let us look at the individual regularization terms. Let me open my pen. So look at this penalty term, lambda times x square plus y square. And for simplicity, let's assume the value of lambda equal to 1. That means the penalty term for ridge, p ridge, is equal to x square plus y square. Here, of course, I'm assuming that the penalty term, I mean, the lambda term has been put as 1. And if this is equal to some constant value, some c square, that means what you are looking at is a set of numbers, x comma y pairs, where they lie on a circle with radius c. For all those points, the penalty due to ridge regularization will be the same. So if c equal to 2, then you are looking at a circle whose radius is 2. And for all the xy points lying on this circle of radius 2, the added penalty due to the ridge regularization will be equal to c square, which is the square of the radius, equal to 4, right? So let us draw a circle like that here. And where is this circle located, by the way? This circle is located at the origin, because if x square plus y square equal to c square, which is equal to 4, you have a circle concentric at origin, and it should be having a radius of 2. So let me draw the circle here. So this is the circle, and we can adjust the radius to be 2, and this is 2. All right. It's not exactly looking like a proper circle, but I hope this is okay for you. Now I'll put this in a different color so that you know that this circle is not one of the concentric circles here from the original loss function. So if I were to mark what is what, these are concentric circles where the normal loss function has a constant value. And this green circle is for penalty term in ridge regression. So penalty ridge equal to some constant number. So now here is the question, okay? If the ridge regression was to make one of the model parameters, in this case y, to be exactly equal to 0, where would the point lie? If you are saying that the penalty due to ridge you want to keep at 4, and which means the xy pair should lie somewhere on this circle, you know that you don't want to pick a point here, because for this point, the penalty due to the ridge regression would be 4. But for this point, since it is so far away from this minima, which is at x equal to 3 and y equal to 0.5, and that is the penalty due to the x minus 3 the whole square plus, I'll write it here, x minus 3 the whole square plus y minus 0.5 the whole square is the penalty due to the original loss term. And I'll just write original loss, and x square plus y square times lambda is there, but I'm not writing it, assuming lambda equal to 1. This is the ridge penalty. So if you are anywhere on this circle, still you might want to be closer to this center than farther. So if you take an x comma y pair here, yes, the penalty due to ridge is still 4 because it's on the circle of radius 2, but you are very far away from origin. So for this point, maybe x minus 3 the whole square plus y minus 0.5 the whole square will be very large. So what about this point? If you were to pick this point, which is x equal to 2 and y is equal to 0, do you think that is the best point? Because if this is happening, then what we are saying is ridge can push one of the model parameters to be exactly 0, because here remember that x and y are not input-output pairs. They are model parameters like theta 1, theta 2. So one way to call this is theta 1. This is theta 2, right? Theta 2 or y, not theta 2 divided by y. So if the model parameter, the ridge regression was pushing the model parameter theta 2, which is y, to be exactly 0, then this may be the point where the penalty remains the same, which is 4. But do we think this is the best possible point here? No. And why is that? Because look at the circle which passes through this point. I can draw a circle that looks like this. So now this is a circle which kind of exactly passes through that point. Okay, so this circle has some loss. So now the net loss is loss due to ridge penalty, which is 4. Net loss equal to 4 plus whatever is the loss due to this concentric circle, and that will be x minus 0.3 the whole square plus y minus 0.5 the whole square for this x comma y pair. And the for all the points along this circle, the original loss term penalty will be the same. But if you are looking at this one specific point, the net penalty will be penalty due to whatever is the value of this orange circle plus whatever is the value of this green circle. Okay. But look at this point now. How about this point? It is on the green circle only. It is still on the green circle, but it is not on this original purple circle which I have drawn. If I have to draw a purple circle which also passes through that point, I have to find a new circle. So let me draw a new circle. So this new circle, which is a little bit more close, I mean, a little bit smaller in radius, can... How about this circle? For if this point is on an inner circle, it means the loss due to the original loss term is a bit smaller. And not just that, the penalty is not increasing. Penalty is still 4 due to ridge because it's still on the green circle, which means the ridge does not have an incentive to push the value of the theta 2, which is the y, and that is a model parameter, to be exactly 0. Ridge does not like to do this, pushing the model parameter to be 0, because there is another point where the loss is the combined loss due to original loss function and the penalty term is a bit lower, right? So this is what you should keep in mind, that ridge regression does not, although for large values of lambda, it can push the value of the one of the model parameters or some of the model parameters to be close to 0. It doesn't push them to be exactly 0. Now let us look at the lasso regression and why lasso pushes the model parameter to be exactly 0. So first I'll delete all of this so that I can clean up the board a little bit. Okay, so now just look at the lasso regression. The original original regression loss term remains the same, but you have a different penalty term, lambda times modulus of x plus modulus of y. Now, if modulus of x plus modulus of y is equal to some constant, it need not be the exact same constant which we chose before. If this is some constant, let's say this constant is equal to 2, how will this look like? How will the graph look like if mod x plus mod y is equal to 2? We can draw a graph that looks like this. So for all these points, mod x plus mod y is actually equal to 2, because here y is equal to 2, x is equal to 0. Here x is equal to 2, y is equal to 0. For all these points, you have mod x plus mod y, or x plus y, because these are all positive numbers. X plus y is equal to 2. You can also have another line which is sort of like this. So this is x equal to 2. Here it is y equal to minus 2. Here also mod x plus y is equal to 2. That is true. Let us draw one more line, or actually I can just copy paste the previous line, something that looks like this. Will also have mod x plus mod y exactly equal to 2, and same for this, right? So if you saw the diamond shape and circle shape from the Google images which I showed you before, so this image, which is very confusing, this is what you should try to understand. What is being plotted here is these concentric ellipses are the loss functions. So loss function meaning isocontours of loss function. So L equal to, so here beta 1 and beta 2 are the model parameters. So here the equation could be 3 times, let's say beta 1 minus 2 the whole square plus 2 times beta 2 minus 0.5 the whole square, something like this. So now you can draw isocontours of this. And what this circle signifies is the boundary of the circle is where beta 1 square plus beta 2 square equal to whatever is the square of the radius. And that is where a ridge regression penalty term has one constant value, the boundary of the circle. Here, this boundary of this diamond shape, which is like a tilted cube, it is where modulus of beta 1 plus modulus of beta 2 has a constant value. Now, this still does not explain why the values in Lasso can be pushed very close to, pushed to be exactly 0 if the, the model parameter is, or if the lambda is very big, or if the model parameter is such that one of the model parameters are relatively small. So we'll have a look at that from this graphical perspective. So let's get back to our diagram. Okay. So now let me draw a point which looks like this. On this point, your penalty due to the lasso, P lasso, is equal to how much? It is equal to modulus of x plus modulus of y, and that is equal to 2. Okay. So for any point, any xy pairs along this blue diamond shape, modulus of x plus modulus of y is 2. So the penalty term due to lasso will be 2. So that is not going to change, which means the total penalty will be 2 plus whatever is the penalty due to the original loss term. And original loss term, the loss of that is signified by these concentric circles. So outer circles have more loss, inner circles have less loss. So let me draw a circle which passes through this point. So this could be a circle which signifies the loss due to original term when you are considering this xy pair. Okay, so now the total loss is 2 plus whatever is the loss attributed to this circle, the circle that passes through that point. But now let us look at another point. Consider this point. This point also has, so I'll delete this circle because this is not needed. So consider this point. This point actually has the same penalty due to lasso because it is also 2. It's still lying on the diamond shape. The xy pair is on this line only. But there is another circle which we can imagine that looks like this, which has a smaller radius. So this circle, which passes through that point centered at the minima of the original loss function, has a smaller radius. And what does that mean? Meaning this point, shown by this pink color, is closer to the center of the original loss function. So what is happening is now the sum total of the loss, which is the penalty due to lasso plus loss due to the original loss term, is lower for this point than for this point. In the previous case for ridge, it was the opposite. So this is why actually, unlike a ridge regression, lasso has a tendency, or it has an incentive to push the model parameter to be exactly 0, like here. So here the model parameter along the y dimension was maybe, let's say 0.5. But here it is exactly equal to 0. But x is equal to like 1 point. Here x is equal to 2. So here the model would rather choose the parameter 2, 0 instead of, let's say, 1.5, 0.5. So there is an incentive for Lasso to do this. So this is why we say that Lasso is like a something that allows you to perform feature selection, because when one of the dimensions are completely cut off, you're not looking at that feature anymore. So this is a graphical intuition which you can always try to have a thought about whenever you see this image. Now let's get back to this image and see what this image is trying to say. This image, what this is trying to say. What this is trying to say is the following. If this is the minima of the original loss function, where these are the iso contours of the loss function. And now if we are looking at any penalty value for the lasso, now you might be wondering, why did we draw this diamond? And in our example, you could ask, why did we define the mod x plus mod 1 to mod x plus mod y to be equal to 2? It could have been 4, it could have been 6, anything, right? So in this website, you have a very, very nice visualization of the loss function where you are not forcing the penalty to be some constant number. So just look at this graph. In my opinion, this is an even better way to understand, but it's slightly complex. So you have to spend a little bit of time. So here, what they have is they have a certain loss function. Ignore this orange parabola for now. Just look at this shaded one, the one with the red to blue gradient. Here, the minima of this function, which is minima of the original loss function, happens at beta 1 equal to like 12 and beta 2 equal to something like minus 12 or something like that, right? So that is where the minima of this function happens, and that is shown by those beta 1 beta 2 pairs are shown by this black cross shape. Okay. Similarly, this penalty term corresponding to ridge, which will be of the form lambda times x square plus y square. Here it will be lambda times beta 1 square plus beta 2 square, will have its minima when beta 1 equal to 0 and beta 2 equal to 0. So here you can see that it's the center of these concentric circles is at 0, 0. Now what happens when these two things are added? Because this is the original loss, this is the ridge loss. You have to multiply with lambda before adding. So what happens? That is what is shown here. So this GIF, please spend like a few minutes on this GIF. I will spend it with you. So here what is happening is, if lambda is equal to 0, then you know that the minima of the overall minima will be exactly same as whatever is the minima of the original loss function. So the minima will be exactly same as this cross. If lambda is tending to infinity, if lambda is very, very high, then what does that mean? That means, let me go back to my loss term example. If lambda is very, very high instead of being 1 or some small number, then the loss term in the ridge equation is dominated by this term. So this becomes kind of insignificant. So the minima of the entire loss function would be whatever is the minima of this guy. And what is the minima of that guy? X equal to 0, y equal to 0. In this example that we are discussing, beta 1 equal to 0, beta 2 equal to 0. So when lambda is very, very, very high, then beta 1, beta 2 for the overall loss to be minimum should be closer to this black dot. What about the cases in between where lambda is neither 0 nor like infinity? Then what happens is, if lambda is some number like 10 or something, then minimizing this means you are increasing the value of this. Minimizing this means, which is like x equal to 3 and y equal to 0.5, means you are increasing the value of this. So your minima will be somewhere between the minima of just this alone, which is at x equal to 0, y equal to 0, or the minima of this alone, which is 3, x equal to 3 and y equal to 0.5. So for all values of lambda, the minima of this L ridge, which is the ridge loss, will be between x equal to 3, 0.5, somewhere between this and x equal to 0, 0. And on the axis, on the graph, how will it look like? This is x equal to 0, 0, 1, 2, 3.5. So this is 3, 0.5. For intermediate values of lambda, the minima of the net function will be somewhere on this line. If lambda is equal to 0, minima will be exactly here. And if lambda tends to infinity, minima will tend closer and closer to this point. And that is what is happening here. So just look at what's happening to these blue concentric circles, which is the location where the entire function is being minimized. You see that initially that blue concentric circle is exactly close to this cross, the center of the blue concentric circles, when lambda equal to 0. As lambda is increasing, you can see that center of those concentric circles are moving closer and closer and closer towards this black dot. You might also wonder, why is this graph rising up? It's because the net loss function can increase when your lambda is becoming higher and higher and higher. So that's the reason why even if you're minimizing the loss function, that minimum value itself need not be 0. It will be a big number because you are increasing lambda, which means you are neither minimizing this nor this. So your the entire L ridge will become 0 if this and this, both of these terms are 0. But you can't have that unless lambda is 0 or unless lambda is infinity. So for all the intermediate cases, meaning all the cases where lambda is not equal to 0, you will have some positive value as the minimum value of the loss function, right? So that is what is shown in this visual. And let me also show one more visual which will make you appreciate L1 and L2 a little bit more. So here I already showed this to you, right? So here these concentric ellipses are those where the original loss function has equal values. So one of these ellipses will, wherever you are there, for any beta 1, beta 2 pairs, you will have the same loss. But now if you look at L1 versus L2 for ridge regression, it prefers a point more like this rather than a point like this, because if you are on this circle, if you are on this dot, you are closer to this minima, which means this circle anyway has the same value of the penalty for ridge, because that is this constant circle is where modulus of beta 1 square plus beta 2 square equal to some constant number. So for the ridge, it doesn't matter where you are on the circle for the ridge penalty. But for the original loss function, it's better if you are closer to this this center dot, which means this point is preferred for ridge, which is L2. For lasso, which is L1, your penalty is the same if as long as mod beta 1 plus mod beta 2 is constant, which is the case with this diamond. And you are better off at this point rather than somewhere here on the diamond, because if you are here, you are farther away from the center. So it doesn't matter for the penalty term wherever you are on the diamond, because penalty is the same on the diamond for lasso, but it matters for the original loss term that you should be closer to the center, as close to the center as possible to minimize the loss due to that. So the combined loss, which is the loss due to lasso penalty plus loss due to the original loss term, could be minimized. So this is why lasso has a incentive to push some of these parameters to be exactly 0, as you can see here. So here beta 2 is pushed to be exactly 0. Beta 1 is positive. But for L2, beta 2 is pushed not to be exactly 0, but something like a small number close to 0, but not exactly 0. So I hope this makes you appreciate, this kind of diagram much better. And now on, I hope whenever you see this diagram, you are not going to feel intimidated. It is saying something beautiful. This diagram is a beautiful diagram. However, it's probably not for the beginners. So I hope the time you spent on this lecture made it worth it. Now let us implement this whole thing using Python code. But since I am yet to formally introduce programming in this course, I will not go through the code entirely. I will just show you the results so that you can appreciate it. So I have coded this in Google Colab, which I can share with you, and you can also try coding it. You can try changing some parameters, and I'll tell you where to change what, right? So this is the code. I'll first run this, show you the result, and then we can play with it. Maybe what I'll do is I'll start the lambda for lasso with 1, lambda for ridge also 1, rest of the parameter, learning rate, etc. are for gradient descent. So no need to focus on that right now, but I mostly want you to focus on the output here, which is the graphs. So look at these these 3 graphs. Let us discuss what each of the items are. These ellipses are ellipses corresponding to our loss function. What is the loss function? I have defined the loss function to be 3x minus 3 the whole square plus 5y minus 0.5 the whole square. Okay, so the minima of the loss function happens at 3, 0.5. Is it 3, 0.5? Yes, x equal to 3 and y equal to 0.5. So that is indeed where you can see the center of this ellipse is lying. Now, if you were to do regression without the ridge or lasso, without regularization, and how can you do that? You can do that by setting lambda equal to 0. Then you should get the minima to be exactly 3, 0.5, and you will see that is what will happen. See, both of them are coinciding at the exact center of this ellipse when regularization is absent. When regularization is present, for small values of lambda, which is 1 and 1, the outcome is slightly different. because you can clearly see that one type of regularization ends up giving you one set of x comma y pairs as the optimum value. Another type of regularization, so cross is lasso and blue dot is ridge. You can see that the optimum at the end of your 100 epochs, so 100 epochs means you are running 100 steps in the gradient descent. I'm not going to go into the details of the gradient descent. It's not important for this lecture, but the outcome is different. That's what you should understand. Now here you are not seeing the effect of lasso pushing the value close to 0. Here still you can see that the value along y-axis is something like 0.4 or something like that, right? So why is the lasso regularization not pushing this value exactly equal to 0? Because that's what we discussed before, right? That generally happens when lambda value is relatively high. So let me put lambda equal to 5 here. Oh, before that, I want to show you the loss. So this is the net loss function for ridge and net loss function for lasso. Both of them will not have the same minima of the loss because both of them are different functions. Different functions will have different minimas. So obviously lasso loss and ridge loss are not going to be the same. If x and y are greater than 1, then for sure x square plus y square will be greater than mod x plus mod y, which means generally here the way we have plotted it, ridge loss will be greater than lasso, and that is what you see here from the blue curve, which is always on top of the red curve. But here I am plotting the final parameters x and y. So here I have two model parameters. Where am I defining that? Here only. In the loss function, the x and y are not input output pairs, they are model parameters, machine learning model parameters. So here I am plotting the final model parameters for ridge and lasso. So blue is ridge and red is lasso. You can see that they are kind of similar, except the parameter which has high value, lasso is a bit higher. Now let me increase the value of lambda a little bit from 1 to 5. So when lambda becomes 5, you can see what happens. You see now the lasso has pushed this value exactly to be 0, whereas ridge is not exactly 0. You can see that from this graph. See, the lasso y has disappeared. The y parameter in lasso regularization has disappeared. Whereas in the ridge, the y parameter, although it is a small number like 0.2 or 0.25 or something, it has not disappeared. Yeah, it is exactly 0.25. Whereas y is like, here it is exactly 0. But here I'm representing it as a small number because the way I have written the function is from scratch. I am not using the lasso package or something. So here I have written it from scratch, but it is essentially 0. So this is the difference between ridge and lasso for larger values of lambda. For larger values of lambda, lasso has a tendency to push smaller parameters exactly close to 0. It acts as selection. So now here essentially lasso selected only this x parameter as the model parameter. The other feature y is now suppressed, completely eliminated. This is amazing, right? Okay, so now so that's the only thing which I want you to take away from this code. I don't want you to focus on the exact detail of the code or anything like that. Now I want to show you one more numerical example with linear regression, where the idea of limiting the value of model parameters can happen when you have regularization versus when you don't have regularization. The model parameters can be too much influenced by outliers. And let us try to understand what this exactly means using a numerical example. So firstly, I'm showing this gradient to you because in the numerical example where I implemented the ridge regularization and lasso from scratch, I had to know the gradient term. So this is the L ridge, and when you do the dou by dou m of this L ridge, this term is straightforward. Dou by dou m of this term is straightforward. For this term it will be 2 lambda m. So that is the additional gradient that is coming in the loss gradient due to ridge. In lasso it will look like this. So in lasso this was lambda mod m. So if m is equal to 0, then modulus is not defined, the gradient of modulus is not defined. But if m is greater than 0, this will be plus lambda. If m is less than 0, this will be minus lambda when you take the gradient dou by dou m of lasso. So I just wanted you to have a look at this to understand that the derivative of lasso is not very straightforward. Also, just have a look at the absence of any model parameter here. So this is simply lambda. So if lambda is 1, the gradient due to lasso, this term is simply plus lambda or minus lambda. Okay. Now let me open the other code which I have implemented. So here I have defined an array where your inputs are 1, 2, 3, 4 up to 10. And in one case, we can have the output also to be 1, 2, 3, 4 up to 10. So if we were implementing a linear regression on this, you should have a straight line which is like y equal to x with slope equal to 1, right? But now suddenly imagine this term was instead of 5, this was 15 or something. Clearly this one is an outlier. The rest of the data is still following the pattern of y equal to x. So if this is 15, what is going to happen to our least square fit line? What happens is the following. We can draw and talk about that a little bit. So if this is your y is your prediction and x is your input, then let's say your data otherwise looks like this. Your linear regression should ideally provide an output that is like this. But imagine this data point was kind of like here. So rest of the data points remain the same, but this one is here. What happens is this line will become something like this with an increased slope. And here slope m is the parameter. And now this increased slope is not good here, because if there were a lot of points here, then we know that all the other points are following the pattern of a straight line which was supposed to go like this. But now just because of the presence of 1 or 2 or few outliers, we are now having a line with an increased slope. And regularization can prevent this from happening. Not prevent, maybe mitigate this to a great extent. So let us run the code with regularization, with ridge and lasso, and also with a normal linear regression, and see how the output differs. Here actually originally I had implemented ridge and lasso from scratch, but this piece of code is implementing it using scikit-learn package. Don't worry about the details. I am yet to cover these things in detail in the course, but let's plot the data set. So if you have the outlier, okay, first let me remove the outlier and run. If we don't have the outlier, we should have the linear regression show something like y equal to x. And let us see if indeed that is happening or not. For some reason I can see an outlier here at x equal to 5. This data set looks okay to me. Let's see. I will copy paste this and run it once again. Okay, so now look at this. The blue line is the actual fit. Ignore the regression, the regularization plots now. Ignore the ridge regression or lasso regression plots right now, but you will see the benefit of that soon. So imagine now this was maybe 20. The ML model that you're using should not try to change its values just because of the presence of this 20, because that 20 is clearly an outlier. See what's happening. Because 20 was present, the slope of this line increased a little bit. Actually, it's easier to see if this is 5 and the last point increases. So let me keep this as 40. So if this is 40, now clearly this blue line's slope has increased because it was supposed to pass through these black dots, but the last dot is now here. So because of this outlier, the dotted blue line slope has slightly increased. And see what ridge and lasso is doing. Ridge and lasso is trying to bring the slope a little bit down. It's trying to mitigate the effect of this outlier. It's not fully succeeding at it because it depends on the value of lambda also. And maybe here we can play with different values of lambda to see what happens. Sometimes it suppresses the parameter entirely. So let's see what alpha equal to 2 can give us. Oh, its range is anyway 0 to 1. So 0.9. Yeah, so 0.9 means this is what is happening, and actually this is not the alpha. X predicted this alpha, not this alpha. I'm sorry about that. So this alpha is 10 and 5. So what if this is 25 and 25? Maybe sometimes fitting will be difficult. So yeah, as you can see in Lasso, it simply eliminated the slope term, and now the slope term is not completely eliminated. It's very small, but you just have the y-intercept. So this is also not good. So too high of a lambda is not helping here. So here maybe what if you use 3 and 5, something like this. This is fine. So you can see that the effect of, since lambda is small in ridge, the effect is not very pronounced. So maybe 10 and 5 was better. These values were better. So you can see that it's not fully mitigating the effect of outlier, but it is doing it to some extent. And the effect of regularization will be even more pronounced if your data set is complex with multiple features present in the data set. So, and you might have seen already that selection of lambda is as if it's a bit like a trial and error, right? So it's actually supposed to be treated as a hyperparameter. So you have to try to find the optimum value of lambda also that minimizes your loss, not just the model parameters. So selection of lambda, there is no thumb rule or anything. It depends on the kind of data set. So what you can actually do is like you do this k-fold cross validation where you train the model on different sets of data and within a given data set. So you use 4/5 of the data for training and 1/5 of the data for testing, and you change which 1/5, whether it's the first 1/2 or the first 1/5 or second 1/5 or third 1/5, that you can change, this is like a k-fold cross validation. And for each of these you may end up getting slightly different values for lambda, and this can be helpful for finding the optimum value of lambda for your model. Try different values of lambda from 10 to the minus 2 all the way till 100. And in general, if you want a sparse model where all the features are not considered, where you want to suppress some features that may be not very relevant, then use Lasso. But if all features you think are important to be kept, then you have to use Ridge. You should not use Lasso because Lasso has good likelihood that it may suppress, it may eliminate some features. And there are some practical recommendations which I have generally found, and a small value of lambda for Ridge is somewhere between 0.01 to 1, and for Lasso it will be something like 10 to the minus 4 to 0.1. And for Lasso, if you keep the lambda small in this range, more features will be retained. But as you keep increasing the lambda, we only discussed so far in this lecture with models having just 2 features, with data having 2 features. But if the data had 10 or 15 or 20 features, like how it is for many practical problem statements, keeping a value of lambda like this may entirely eliminate some of the features that are unimportant. So if you want to eliminate some unimportant features, keep this. If you don't want, keep this range of lambda. And of course, this will depend on the data set. So I'm just giving this as a practical thing, which I have generally seen when I work with some data sets. But other than that, I think this is a good time to wind up this lecture on regularization. It's a fascinating topic. If there is one thing that you want to take away from this lecture, it is the intuition behind this plot. Intuition behind why Lasso makes some of the parameters shrink entirely to 0, whereas Ridge does not do that. So with that, let us wind up the lecture. I am so happy that you are following with me throughout this course, and I'm so glad that you have reached a point where a lot of things are now covered, and I'll be looking forward to seeing you again in the next lecture. Take care until then. Bye.